Let's look at a nonlinear example. We're taking this 2D ODE, and we're looking at something a bit more complicated than the pendulum, but it's something that doesn't really have as easy of a correspondence in a physical problem. So we have x prime equal x minus 4, 3 minus y, and y prime is equal x minus y, x plus 2. The first step is to find critical points. So we want x prime equal to 0 and y prime equal to 0. If we have x prime equal to 0, well, we already have the division in factors, so we need each factor to be equal to, at least one of the factors to be equal to 0. So we either need x minus 4 equal to 0 or 3 minus y equal to 0, that is, y equals to 3. The other equation that we need to solve is y prime equal to 0. That gives us either x minus y equal to 0, so x equal y, or x plus 2 equal to 0, so x minus 2. Now that we have x prime equal to 0 and y prime equal to 0, we need one of each, because choosing either will put to 0 the corresponding derivative, so we pick one from one side and one from the other. So we can pick x minus 4 equal to 0 and x equal to y. So we have a critical point that is 0, 0. Or we can pick x minus 4 equal to 0 and x plus 2 equal to 0. We cannot solve both, so that doesn't give us any critical point. We have y equals to 3 and x equal to y. That gives us the critical point 3, 3. And then the last combination is y equals to 3, x equal to minus 2. That gives us a critical point minus 2, 3. So now we have looked at this nonlinear ODEs, system of ODEs, and we have found 3 critical points that we can plot like this. 3, 3, 4, 4, minus 2, 3. The next step is trying to understand what is happening in the graph. So what we want to plot in the graph is what is called null lines. That is, curves in our graph where only one of the derivatives is equal to 0. So as before, we divide x prime equal to 0 in two factors, either x equal to 4 or y equal to 3. Either of these give us a curve in which x prime is equal to 0. And x equal to y and x equal to 2, either of them gives us a curve on which y prime is equal to 0. So what does that mean? That means we can draw the line y equals to 3 and the line x equal to 4, and we know that it's on these two lines x prime is equal to 0. That means that any point on this line has derivative of x equal to 0. That means that any point in here, in these two green lines, only moves vertically, because y prime might not be 0. We don't know if it's positive, negative, or whatever. Might be whatever. But we know that it is that x prime is equal to 0. So the only direction in which we could potentially move is the vertical direction. In the horizontal direction, we cannot move because the derivative of the horizontal direction is equal to 0. And the same thing we do with y prime equal to 0. We create these two lines, x equal to y and x equal to minus 2. And these two lines, we know that y prime is equal to 0. That means we cannot move vertically on the red lines. We only move horizontally. So if we can associate this graph with some ticks on the four null lines I just drew. The red lines, where y prime is equal to 0, we are only moving horizontally. The green lines, where x prime is equal to 0, we're only moving vertically. Now that we have this division, this first understanding of what things are happening, what we want to understand are the signs of x prime and y prime. So we already know that the plane is divided by these null lines. That means that these lines are the only point in which x prime is equal to 0. Everywhere else, x prime is different than 0. That means that these null lines are dividing the space in 4 areas, each one of these areas has the same sign of x prime. Why is that? Because of continuity. If the value of x prime is something in one of these areas and you move inside that, it's not going to cross 0 because it only crosses 0 on the null lines. So inside these areas, inside any area bounded by null lines, the sign of x prime is constant. Now I can pick any point, any point inside these 4 areas and determine the sign of x prime. You can do it however you want. For example, in the green area, you pick 0, 0 and just check the sign. And you can pick one point in each of these areas to determine the sign. So now we have an understanding that in these 4 areas, we know the sign of x prime. That means we know that everything, for example, in the green area is moving towards minus infinity in the x direction. We don't know how they're moving in the y direction yet, but we know that the green area is moving to the left. The orange area is moving to the right, and so forth. For each one of these 4 areas, we know in the horizontal direction how they're moving. So we can draw it with some arrows to indicate each one of these blocks in which direction is moving. Now we can do the same thing with y prime. We have these 2 null lines. So we know that there are these 4 areas in which the sign of y prime is always the same. So we can pick any point inside these areas and determine the sign of y prime in here. And the sign of y prime gives us some information about how you're moving in the vertical direction now. So for example, in the green area, we found that the sign of y prime is positive. That means that y is increasing in this green area, but it is decreasing in the yellow area, for example, because there we found that y prime is smaller than 0. In the middle, we have the null line that is dividing the areas in which y prime is positive and the areas in which y prime is negative. So now again, we replaced our information about the sign of y prime by some arrows indicating if we're moving up or if we're moving down. And we have information about x. We have x prime moving left or right. We have information about y prime moving up or down. And now we want to take these 2 information that we have plotted into different graphs and just merge them. Put them together in only one graph. And because of the null lines, we have divided our phase plane, our 2D plot, in areas in which, if you're considering both the null lines with respect to x and the null line with respect to y, each section of our phase plane has only one combined direction between x and y. For example, at the right bottom, we have y prime is positive and x prime is positive. So we're tending up and right. We're really just mix and matching what is on the sections on our graph with the things we have found about x prime and y prime. It looks something like that. It might be a bit confusing, but it's a direction field. It means that any point you can start on in this plane is going to be following these arrows. So for example, if I start at 3 minus 2, we are going to go up and left. Then I'm going to cross the horizontal line that is x equals to y, and then probably going to be going down and left, and then horizontal and left, and then up and left, straight up, right and left, and then some other things are going to be happening, but it might not be super precise where exactly I'm going, but I start having a vague understanding about what is what. And I can do the drawings a bit more clearly in order to have like more arrows, all of the same size, and understanding a bit better. In here, we can start talking about trajectories. A vague understanding, we haven't really solved the ODE, but it gives us some understanding that, well, if I start on the bottom of the blue line, I'm going to follow the blue line and do something roughly like that. If I start at the bottom of the green light, I'm going to follow the direction field like that instead. So specific solutions are called trajectories. In this case, we have the fact that these two, green line and blue line, look extremely different. They behave in a different way. And in the middle, we have this yellow line of only vertical elements that goes straight up, because x prime is equal to 0 on the green line, on the null line. So there is this yellow trajectory that is dividing the behavior of the blue trajectory from the behavior of the green trajectory. We call this yellow line a separatrix. Separatrix are really interesting to find, but also really hard to find, because they give us an understanding of where the distinction is between some type of behavior and some other type of behavior. We can also talk a little bit more about basin of attraction. For example, if at this point that is -2, 3, we have an equilibrium, a critical point. If this critical point is asymptotically stable, that I haven't really proven, I'm just gonna have been telling you that it is, then it has a basin of attraction. What a basin of attraction is the sum of all the points that over time are going to move towards it. A basin of attraction is a stronger information than a stability area or asymptotic stability, because it doesn't need to be a ball. For example, some elements, anything downwards from that point, over time is going to get to that point. But if you move right from that, there are elements that will never get there. So a basin of attraction can have really weird shapes. It just gathers all the points that over infinitely long time are going to get to an asymptotically stable point. We're not going to talk about the fact that a basin of attraction can be very weird, not yet. But we're going to be talking about the concept that a basin of attraction stops by a separatrix. So if you're growing this blue area as far as possible, you're going to notice that it bumps into this yellow separatrix we had built before. We haven't actually built the top side, but that is also a separatrix. It divides the full plane between things that will likely tend to infinity, or we don't really know what is going on in there, and things that tend to our asymptotically stable point.